Why do we mix? If you change the powder and polymer, what is changing in the way you mix things? So mix material effects. What are some equipment with which you can do mixing for different systems? Because dry mixing, right, is different from mixing in a polymer solution, is different from mixing in a polymer melt, right? In one case, it's referred to as blending when it's all just solid. When you're dealing with a solution, when it's a solution, you're dealing with no temperature or less temperature. And because of the lower molecular weight of the solvent, you're dealing with lower mixing forces required to get a homogeneous mixture. But then when you're dealing with melts, you need to heat up the material, and polymers will have a higher viscosity compared to a polymer solution by itself, right? Because the lower molecular weight solvent doesn't exist. So the mixing intensity, right, the shear force that you have to provide is going to be higher. And so because of that, the design of the mixer is going to change depending upon what system we are mixing. And of course, those three limiting cases, solid, solution, melt, are the three different cases in which we are going to make different shapes, right, for different applications. So different mixers are going to change, right? If your material is changing and your process is changing, the uniformity of the mixture, the homogeneity of the mixture is going to change. Firstly, how can you tell this is better mixed than that mixture? We need to have a way to do that. How can you tell? And then from a simulation perspective, how can you predict it beforehand and try to get the combinations right with lesser trial and error, right? That's the other way. And then finally, how to know how much to mix, how much powder to put in the polymer solution or in the polymer melt, because you want some processing attributes, some properties. We looked at rheology in one hand, but it can be thermal conductivity, it can be heat capacity, right? We need to know what those properties are and how to predict that as well with these models so that you can control the process. If I mixed A and B and got a mixture, and okay, I got it homogeneous, can I make a shape with it, with this process, is the question. And so whether the answer is yes or no depends upon what are the properties. If it doesn't flow well, then it's not a suitable mixture and you got to create another mixture, right? If the thermal conductivity is too high and it's a melt and you're putting it into a mold cavity, even if you have good viscosity, what happens to the mixture if the thermal conductivity is too high? It's going to lose heat more rapidly, right? And so maybe it solidifies faster than before completing the whole filling of the mold cavity to create a shape. So you get an imperfect shape, right? So controlling rheology, on the one hand, you want to fill it fast enough, but you also want to make sure that it doesn't lose heat too rapidly. So thermal conductivity, heat capacity is the reverse, right? Ability to hold heat, thermal conductivity is the ability to lose heat, right? Those have to be balanced out in a mixture. So these kinds of properties become important. And then depending upon the nature of the process, right? Just like in chemical engineering, you deal with PVT, pressure, volume, temperature relationships, when you're dealing with liquids and gases. You have to deal with those properties when you're dealing with polymer mixtures as well. Okay, so that is basically the kind of ground that we will try to get some initial ideas as to you change the powder and polymer, what happens to the process, what happens to the mixture, how can you control it, right? How can you characterize it, right? That's the agenda for right now. So polymer properties can be modified, we saw that. And so that is one context. And you can either change the molecular structure. What is an example of this? Cross-linking, right? So that is one way, right? And in the case of rubber, right, you add sulfur as an additive and you can cross-link. Or you can change the stiffness, you can add glass fiber, you can add clay particles, and you can change that. This is a micrograph of carbon particles in synthetic rubber that's used in a tire. And you can see that some regions are dispersed, some are agglomerated. And these particles are typically in the order of about 100 nanometers or something like that. Okay. So dispersion is going to change properties. And sometimes you disperse it well, sometimes you don't. And so accordingly, properties are going to change. And so sometimes you will have a tire that bursts suddenly if the speed is too high, or the temperature is too high, or the road is too rough, and then there's an accident, and then there's a lawsuit, right? So comes back, if you didn't have the right carbon, you didn't have the right dispersion, you didn't have the right curing temperature, you're going to make a defective tire, right? And that can result in loss of life, from time to time you hear 5 million tires recalled or something like that, and you can imagine what is the loss and what is the penalty in case they are not recalled, right? So mixing matters. Right? That was in case of particles of carbon in a polymer. You can also want to mix two different polymers and create blends to give combination of properties. And again, in that case, sometimes you will have domains of dispersion that are different, and then you have like domains that are different like this. And so uniformity, whether you're putting powder or mixing two polymers, becomes a challenge. One thing we looked at was you might need to use a combination of additives, combination of polymers in powder processing. Lower molecular weight, better viscosity, higher molecular weight, better strength. And so you might need to mix two different polymers to get a combination of good flow properties, and once it has become a solid, good strength, so you can take it out of the mold, right? And so just like you had to worry about powder dispersion, you had to worry about how two polymer phases disperse as well, right? So you have all kinds of different things to change properties in the conventional case, right, of additives. And so a lot of technology related to mixing had a lot of progress in this context in the plastics processing industry. Then when you began to add powders, one thing we said was we need to have a high volume fraction of powders in ceramic or metal powder processing. The second thing is these are more abrasive materials, and so those are some changes you have to make. You have a high solids loading, what happens? A high volume fraction of powder, what happens to the mixture? The viscosity is too high. Viscosity is too high, it becomes more difficult to mix. Correct? So that means you might need a new mixer geometry. Right? Or it is a lot easier to get poorly mixed materials when you're dealing with our set of processes. And so the agglomeration dispersion becomes a big issue. You reduce particle size and increase surface area, as in the case of beginning to emerge into the domain of nanoparticles. These issues become even more important because interparticle forces become even more dominant. So ability to mix or disperse becomes more challenging as you go into the nano domain, and so something to pay attention to. Sometimes some of the projects that I've done is adding tungsten to polymer. Tungsten has a density of 19.2 grams per cc. Polymer has 1. Lead has about 11.2. So if you have right amount of lead, right amount of tungsten in polymer, you can get the density close enough to lead. It's useful for shotgun shot. It's useful for wherever lead is used, balancing weights on wheels, X-ray shielding. And so the toxicity of lead is circumvented by going to filled polymers. Okay. This is a catalytic converter, the substrate that is used in cars near the exhaust. It is a ceramic that is extruded. Typically, the cell size over here is about somewhere between 50 and 100 microns, okay, depending upon the complexity. And now that surface is coated with a catalyst, and exhaust gases coming around can get burnt out more completely, and emissions can be controlled. Right? So mixing is, and these are all different kinds of injection molded components out of stainless steel, which are more complex in shape, right? And now you're dealing with high volume fraction of powders, and this is the area that we'll focus on. Right? So to connect the context of mixing to the starting materials, we have to first deal with the fact that you have different materials of shapes and sizes, different packing forces, right? Different viscosities. Right? And so how much powder you can mix is affected by this packing fraction, which is particle size. That's one thing that we looked at. And so that begins to, so if you operate in this region, it's going to be harder to get a good mixture. So yeah, you can make the shape easily by having lower viscosity, but once you burn out the polymer or dissolve it off, what is holding the powder together? It's just powder-powder interactions, right? So the more powder there is, at that stage there's more strength in the shape before it sinters and bonds begin to develop. And so on the one hand, to make the shape, you want to make it as low a viscosity. On the other hand, after you remove the polymer, you need sufficient strength, and you've got to operate in the space over here. If you operate in the space, see, small changes in volume fraction of powder result in large changes in viscosity. Right? So the room for error is very low. Right? So another aspect of mixing is how to control the relative ratio of powder and polymer within a very narrow window, because small errors can result in small errors in volume fraction can result in large errors in viscosity. So the ability to make or not make a shape can be quite different if your mixture is not homogeneous enough, uniform enough, right? If some regions of a batch have more powder and some regions have less powder, if you're doing a mass manufacturing, some parts will be defective, some parts will not be defective, and that poorer the mixture, the greater the defect population, and there's nothing you can do to change it in the molding machine, right? And so mixing uniformity, because of the sensitivity to changes in viscosity, are very high with small changes in volume fraction. That becomes a specific challenge to address.